Okay, so at the end of the last video, we were just getting the answer to number 6 when the video finished. So in case you didn't get it, it was 3.71056 times 10 to the 19th joules. Okay, so that was number 6 on page 570. All right, so the photoelectric effect, we spent a fair bit of time on it, and we have for two reasons. One is because, remember, it was one of the two key experiments that caused us to go back and say, wait a second, what is light really? And the photoelectric effect, and the other one that we're going to do later in this video, cannot be explained when one thinks of light as a wave. The only way one can explain what's happening in the photoelectric effect is if one thinks of light as a particle. Okay? And so it opened back up that debate, what is light? That debate that eventually gets settled by Albert Einstein, who says light has a dual nature. Sometimes light acts as a wave, and it does that when it's interacting with other light. And sometimes light acts as a particle, and it does that when it's interacting with matter, which is what it's doing in the photoelectric effect. But there's a second reason that I wanted you to understand the photoelectric effect as well as possible. And that's because even though it was worked on in the turn of the century, so we're talking like 1900s, like probably up to about 1924, from 1900 to 1924. Once we figured out what was going on, it opened up a wide array of possibilities, a wide array of inventions. You use the photoelectric effect a ton of times in your life on a daily basis. So there are lots of items that you encounter in your life that have an incomplete circuit in it, and that circuit is only completed by light shining on a photosensitive surface. And if something gets in the way of that light shining on the photosensitive surface, if something blocks it so that light can't get there, then whatever the item isn't able to work. So if you think for a second about like a garage door opener, or at least in the olden days, I don't know how they work now, and the same for a TV remote, right? You shine infrared light on a photosensitive surface, and that completes a circuit that then causes either the television to turn on or the garage to open. If something happens that blocks that light, if you put a piece of paper in front of your TV remote, then it isn't going to open. Right? The light isn't going to get there. It isn't going to create the circuit. The TV can't turn on. Same with the garage door opener. There are lots of garage doors where they won't come down even once you've pressed the button if there's something in the way, something that's blocking the light from going from one side to the other. Elevator doors are the same. The infrared light goes from one elevator door across to the other where the photosensitive surface is. If your leg, your body, your arm is in between here, then the circuit can't be complete and the door won't open. If you've ever broken into an art gallery, which hopefully you haven't, the security system in art galleries and banks and all those kind of places is a laser beam that starts at one wall and shoots across to the other. And you see this in like Pink Panther and all those kinds of movies where there's someone trying to steal the expensive diamond. So the laser beam goes from one wall to the other, and on the other wall is the photosensitive metal. And as long as the laser beam's hitting it, then there's a circuit that's completed and the alarm is good. But as soon as something blocks that laser beam, so it's no longer hitting the photosensitive metal, the circuit is no longer completed, and the alarm sounds. Scanners in a grocery market are the same. Those speed signs, you know, the ones that they post where they flash your speed up. You know, you're going through a school zone and it flashes how fast you're going, based on the photoelectric effect. So are street lights. So if you have a minute or two at some point in the next couple of months of your lock-in, Google uses of photoelectric effect today. There are a ton of them. I've just named a couple here, but you will be 100% surprised at how many there are. Okay, so that's one of the two experiments that caused us to go back and reevaluate light. The other one is called the Compton effect. The Compton effect is named after Sir Arthur Compton. And Sir Arthur Compton, I think it was around 1922. And what he did was he took a high-speed photon, high energy, excuse me, all photons travel at the same speed, a high-energy photon. And remember, high energy, remember energy of a photon is equal to HF. So if it's high energy, then it means it's high frequency. Okay, so there's going to be like a lot of waves in a given path. So a high energy photon, and he shoots it at a surface, and what happens is that a little electron gets fired off as a result. Now, remember that a photon is like a little packet of energy. It's a little packet of light. Think of it like as a Ziploc bag filled with light. It doesn't have any mass because it's light, but it's acting like a particle. And so it strikes the surface, and a photon gets fired off at some speed. And if it has some speed, then it has some momentum. So there's a collision happening here between the photon and the electron gains momentum as a result of the collision. Well, that's pretty normal if we think back to grade 11 and grade 12 physics. One object hits another, there's a transfer of momentum, and we know our law of conservation of momentum says momentum is always conserved. The electron also picks up some kinetic energy, so we know it must get both of those from the photon. The thing is, the momentum is P equals mv. The photon doesn't have any mass, it's light. And actually after this collision, there is a lower energy photon that is also given off. So it's clear that it's lost some energy to the electron, so that's not surprising. But it's like, how did it lose momentum? How did it give momentum to the electron when it didn't have momentum to begin with? Okay, so we know that no particle that has mass can travel at the speed of light. And we know that a photon is light, a little packet of light. So we have to assume that it has no mass. We often talk about it has no rest mass, meaning like if you could stop it, slow it down, it wouldn't have any mass. And yet somehow it has energy and momentum. And so in the end, this led us to define the momentum of a photon. Define means we said, okay, like we can't measure it, we can't we can't derive it. We can define it. So we define it as the energy divided by the speed of light. And we know the energy of a photon is hf, and we know the speed of light is f lambda. And so the f's will cancel, and we get the energy of a photon to be h over lambda. Okay? So this is our equation for energy of a photon, and it is not dependent on the speed of light. If we look at the units, h is joule seconds, wavelength is meters. And we know from work is equal to F delta D cos theta that a joule is a Newton meter. So this is a Newton meter second over a meter, so the meters cancel. And we know from F equals ma that a Newton is a kilogram meter per second squared. So this gives us a kilogram meter per second squared times a second, which is a kilogram meter per second, and that is what momentum is measured in. Okay, so that's our equation for momentum this evening. More questions on the photoelectric effect. So, and one with this, so page 571, numbers 7 to 13. Okay? All right, very good.